Dear students, welcome to the online class. I am Dr. S.S.C. Hiremat. In this video, you are going to study about the Lindemann's time-lag theory of unimolecular reactions. This theory was proposed by Lindemann in the year 1922. He explains how a bimolecular collision can give rise to a first-order reaction or a unimolecular reaction. About postulates of this reaction. Postulates. First, activation of molecules by collision. Reacting molecules collide with each other and there is the exchange of energy. Then some molecules absorb the extra energy. That extra energy absorbed is called the energy of activation, and such molecules are called the activated molecules. But according to this theory, the activated molecules are formed by the collision with the other molecules. Then second one, that is time lag. The activated molecules must have the minimum survival period. If it is more than that, and they collide with the other molecules, they can give the product. Otherwise, they do not give the product. That minimum period is called the time lag. Okay, time lag of the excited species decides whether it can give back the products, reactants, or it can give the products. Then third one, the deactivation. Activated molecules may deactivated to give back the reactants or to give the product. Means deactivation of the activated molecules takes place by two processes. They can give back the reactant molecules when they collide with the other molecules, and similarly when they collide with the other molecules, they can give the products. Thus the deactivation takes place by two processes. Then fourth one, rate of deactivation to give back the reactants. Means when the activated molecules collide with the other molecules, if their life is less than the time lag period, then they can give back the reactants. Then the rate of this reaction is directly proportional to the concentration of activated species. Then fifth one, rate of deactivation to give products. If the life of the activated species is more than this time lag period, when they collide with the other reacting molecules, then they can give products. Means the activated molecules which can survive for a period more than this time lag, when they collide with the other molecules, they can give the product. Otherwise, they don't give the product. By these postulates, we can derive the expression for the rate of a unimolecular reaction according to this theory. That is mechanism. The mechanism of this theory consists of three steps. That is step 1. The reacting molecules collide with each other. Means A is one reacting molecule collide with another reacting molecule, and one activated species is formed and another reacting molecule A is formed. This reaction takes place with rate constant K1. This is a formation of activated species. That is step 1. Then step 2. The activated species A star collide with another normal molecule and gives rise to normal molecules or the ordinary molecules. That is deactivation. This step 2 is deactivation, just the reverse of the step 1. And this reaction takes place with rate constant K2. Then step 3. The activated species collide with the other molecules and gives products. Or they give the products. And this reaction takes place with rate constant K3. Thus totally this mechanism consists of 3 steps. Here the intermediate compound or the activated species complex, this is A star involved in all 3 steps. We can apply the steady state approximation to this species, that is applying steady state approximation to A star, we get that is d A star by dt at a particular period. The rate of formation of A star is equal to rate of absorption of A star. Thus the rate of formation of A star is by equation 1, step 1, K1 is into concentration of A raised to 2. By this the A star is formed, and here the A star is absorbed. That is rate of absorption of A star by this process is K2 into concentration of A star into concentration of A. Then the rate of absorption of A star by this process, that is minus K3 into concentration of A star. Okay. Then according to the steady state principle, at a stage this is equal to 0. Means the rate of formation of A star is equal to rate of absorption of A star, so that the change in concentration of A star remains constant. Then on rearranging this, we are going to get K1 A square is equal to, you take this to the right hand side, then you take the common A star into bracket, that is K2 into concentration of A plus K3. On rearranging this, we are going to get, that is A star concentration of A star equal to K1 and A square divided by K2 A concentration of A plus K3. This is equation. We may give equation number to this equation as 1. Then rate of this reaction is decrease in the concentration of A or the increase in the concentration of the product. Thus the rate of reaction can be expressed by any one of this method, that is rate of the reaction is that is dA by dt, which is equal to dA star by dt. Here dA by dt is the decrease in the concentration of A, and dA star by dt is the increase in the concentration of the product. Thus the rate of reaction can be expressed by any of this, and this is more convenient, that is rate equal to dA star divided by dt. This is by step 3 equation, that is K3 into concentration of A star. By substituting the value of A star in this equation, we get this is equal to K3 into A star equal to K1 A square divided by K2A plus K3. This is nothing but dA naught divided by dt. this is equal to this. This equation can be numbered as 2. Equation 2. This is the expression for rate of this reaction. Okay, these are the 3 steps of the mechanism, and rate of this reaction is this. Now we can apply the conditions for this. Here, if the rate of this reaction is more than rate of this reaction, that is case 1, we can apply. Rate of this reaction is nothing but that is K2 into concentration of A star into concentration of A is greater than K3 into concentration of A star. Case 1. Okay, rate of this reaction is more than rate of this reaction. Thus, it gets cancelled. A gets cancelled. Then we get K2 concentration of A is greater than K3. Then, if we substitute the value in this reaction, if K2A is greater than, very greater than K3, thus it is negligible. Then equation 2 becomes that is dA naught divided by dt equal to K3 into K1 into concentration of K2 into K2 into concentration of A. Thus this A and this 2 gets cancelled. Then this is equal to K3 into K1 divided by K2 into concentration of A. Okay, we may give the number 4 to this. Equation 4 shows that rate of this reaction is directly proportional to the concentration of A. It is equal to directly proportional to the concentration of A, or which is, we may substitute this taken as a constant K dash and which is equal to this. Thus, from the equation 3, it shows that the reaction is of first order and rate of this reaction is larger compared to rate of this reaction, or rate of this reaction is negligibly small compared to the rate of this reaction, then the reaction is of first order. Okay, and this is first order. Now another condition we may place, that is case 2. What is that? This is smaller and this is larger. Then that is K2A is smaller than K3. And you substitute in this equation, you can neglect this. This is negligible and this remains constant. Then you are going to get, then equation 3 becomes, that is dA naught divided by dt, that is dA naught divided by dt is equal to that K1 divided by K3 into concentration of A square. Okay, the same may be written as this is equal to some, that is K1 into concentration of A square. Thus equation 4 shows that the reaction is of second order. Means if the rate of this process is less than rate of this process, then the reaction follows second order. Okay, thus a reaction may be a unimolecular or first order, or a reaction may be second order. It depends upon the rate of second step and rate of third step. Okay, an unimolecular reaction may be, according to the Lindemann's TimeLag theory, it may be first order, if this is dominant and this is negligible, and the reaction is second order if this is negligible and if this is dominant.